When we talk about matter, we first have to separate it into two big groups. Today, we're focusing on a substance, also called a pure substance. Think of it like this. A substance is perfectly clean, uniform, and consistent. It's matter that has the exact same composition and properties everywhere. Pure water, for instance, is a substance. Every tiny bit of water is H2O, and it will always act like water, no matter where you find it. Pure substances break down into two categories. First, we have elements, which we talked about in the last lesson. Stuff like pure gold or oxygen gas. They are only made of one type of atom. Second, we have compounds. A compound is formed when two or more different elements are chemically bonded together, like sodium and chlorine forming table salt. Even though salt is made of two elements, the resulting compound, NaCl, has its own unique, uniform identity, so we consider it a pure substance. Now let's look at the flip side. Mixtures. Unlike a substance, a mixture is just a physical mashup of two or more things. Imagine stirring sugar into water, or mixing sand and pebbles. The components are still there. They haven't chemically bonded, and they keep their original properties. A mixture of sand and water is still sand and water. Because it's only a physical blend, you can usually separate a mixture using physical means, like filtering the sand out of the water. To identify and tell the difference between all these substances and mixtures, we use properties. A property is just a trait or characteristic. It's anything you can observe or measure about the substance. Think of properties as the unique set of features that define something, like the color of your eyes or the sound of your voice. In chemistry, these properties are how we identify the who's who of matter. Some properties are more useful than others for identification. We rely on characteristic properties. These are the properties that are constant and unique to a specific pure substance. Crucially, they do not depend on the size or amount of the sample. For example, if you have a huge block of gold or a tiny speck of gold dust, the color is the same, but the mass is different. Characteristic properties are the constants, the reliable scientific fingerprints. We categorize properties into two main buckets, physical and chemical. The key difference is the concept of change. A physical property can be observed without changing the substance's chemical identity. You're just describing what it is. A chemical property describes the substance's potential to undergo a transformation, meaning you have to actually change it into something new to observe the property. Let's dive into physical properties. These are things you can see or measure easily. Is it solid, liquid, or gas? What color is it? Can it dissolve in water? We look at things like hardness, flexibility, and conductivity. But the most important physical properties for identification, the characteristic ones, are three measurements that are constant for any pure substance: melting point, boiling point, and density. Density is one of the most powerful characteristic physical properties. It tells you how tightly packed the matter is in a specific volume. We calculate it by dividing mass by volume. D equals m over v. A styrofoam cup and a small rock might take up the same space, but the rock has much more mass, so it's much denser. Because the density of pure gold is always the same, no matter the sample size, it's perfect for identifying the element. Next up is melting point, MP. This is the specific temperature at which a pure solid turns into a liquid. Imagine you have a mystery solid. If you heat it up and it melts at a precise, known temperature, you've just narrowed down its identity. Pure ice always melts at 0 degrees Celsius. If your ice cream melts at 0 degrees Celsius, well, you probably have some impurities in that ice cream. Similar to melting point, the boiling point, BP, is the specific temperature at which a pure liquid turns into a gas. This, too, is a highly reliable characteristic property. At sea level, pure water always boils at 100 degrees Celsius. If you were boiling a sample, and it started bubbling and steaming at 95 degrees Celsius, you would immediately know that your sample is either impure or it's not water at all. Now for the exciting side, chemical properties. These describe a substance's potential to react and transform into something completely new. To observe a chemical property, you have to cause a chemical change. For example, you can't just look at a piece of wood and say it's flammable. You have to light it on fire to see that chemical property in action. Once the wood burns, it's no longer wood. It's ash, smoke, and gas. A great example of a chemical property is flammability. It's the ability of a substance to catch fire. It is a chemical property because when something burns, its molecules are completely rearranged. The original substance is gone, and new substances like carbon dioxide and ash are created. Gasoline has a high degree of flammability, which is a key property that makes it useful as a fuel. Another important chemical property is reactivity. This tells us how easily a substance will chemically combine or interact with another substance. Remember the alkali metals from the last lesson? They are extremely reactive with water because they desperately want to shed an electron. In contrast, the noble gases have very low reactivity. They are stable and happy, which is why they don't easily form compounds. So why do we bother learning all of this? Because if you're given an unknown substance, you can identify it by measuring its characteristic properties. You measure its density, its melting point, and its boiling point. Then you simply compare those constant numbers to a known table of element and compound properties. If your unknown substance has a density of 19.3 gram per cubic centimeter and melts at 1064 degrees Celsius, congratulations, you've identified pure gold. The use of characteristic properties is vital in real-world jobs like forensic science. When a crime scene technician finds a tiny paint chip or a shard of glass, they don't know what it is. They measure its unique properties, like density or how light bends through it, to create a scientific profile. This profile acts as the evidence, allowing them to match the sample to a specific source, like a car at a particular location. In manufacturing, properties are used for quality control. Companies that make things like metal alloys or pharmaceuticals need to be sure their product is pure and consistent. They regularly test properties like melting point. If a batch of steel is supposed to melt at 1500 degrees Celsius but melts at 1450 degrees Celsius, they know the chemical composition is wrong and the product is faulty or impure. It's essential to keep straight the difference between a physical change and a chemical change. A physical change is just a change in appearance or form. Cutting paper or melting ice are physical changes. The paper is still paper and the water is still water. A chemical change is where a chemical reaction occurs and the starting materials are converted into completely new substances, like baking a cake or setting off fireworks. How do you spot a chemical change in action? You look for key evidence. Did the substance produce gas bubbles when you weren't expecting it? Did it suddenly change color, like a copper penny turning green? Did it suddenly get really hot or cold, or produce light? All of these are clues that a chemical reaction has taken place, and you now have a brand new substance with its own brand new properties. Let's quickly compare one more time. Think about water. If you boil water to create steam, that's a physical change. The steam can cool back down to liquid water. But if you run electricity through water, electrolysis, to break it down into hydrogen gas and oxygen gas, that's a chemical change. You started with one substance, water, and ended with two completely different substances, hydrogen and oxygen, that have brand new properties. To wrap up, the main takeaway is this. The whole world of chemistry is built on the concept that every pure substance has a unique identity defined by its characteristic properties. By measuring a few key properties, like density, melting point, and boiling point, You hold the key to identifying any pure substance in the universe. These properties aren't random. They are constants that give structure to the entire field of matter.